Okay, welcome to topic 4. We're going to be talking today about acceleration analysis. So acceleration analysis is the most difficult topic that we're going to discuss. It's the most math, so hopefully you're bringing your A game with this one. So remember, everything starts with position analysis. Which, you give it some input angle and then you can calculate the position of everything else. And then there's velocity analysis that you give it, at some instant, you give it a velocity. And then with that velocity, you can calculate the output velocities of the other links. And then there's acceleration analysis, which once you've done position and velocity analysis, now you need to be told the acceleration input, and you can calculate the acceleration of all the other links. So that's essentially acceleration analysis. You have to, just like velocity analysis, you have to do position analysis first. You have to do position and velocity analysis before you can do acceleration analysis. Okay, so that's a little intro. Here's the suggested reading in the book. Again, it's just a suggestion. Okay, we're going to first start. You've noticed a pattern. We've done position of a point, velocity of a point. Now we're doing acceleration of a point. And then we did the position difference vector, the velocity difference. We'll do acceleration difference. And then we'll do, just like we did apparent position and velocity, we're doing apparent acceleration. Okay, and you'll see how everything builds off of itself. So we'll start with acceleration of a point. Okay, so imagine this point P here that's zipping around this path, and it's going at this instant in time, in that position, it's going some velocity Vp. And then at a delta t later, you have your P prime position, and it's going to velocity Vp prime. Okay, and that velocity is, of course, it could be, it's definitely a different direction, because remember, velocity always follows tangent. Instantaneous velocity is always tangent to the path. And the magnitude could also be different. It may be the same, but it could be different, okay? But for a general scenario, imagine if you take the Vp prime and you subtract it from Vp, then you calculate delta Vp, which is the change in the velocity vector. So you're basically taking this vector and subtracting it from this vector, and that's delta Vp, points from, the initial to the final, right? And remember, the location of the vectors don't matter, because vectors only have direction and magnitude. So we can align it in this kind of configuration here. Okay, so if you then take that velocity and that change in velocity and divide it by the delta t it took to get from there to there, then you get the average acceleration, right? And of course, that doesn't point tangent to the path or anything interesting. But if we take the delta t and make it go to 0, infinitely approach 0, then this becomes a derivative, the derivative of Vp with respect to time, and that is essentially the instantaneous acceleration at point P. So you can see if the delta t gets smaller and smaller, this can't get as far away, and you get the acceleration here at AP. Okay, which, by the way, it's worth noting that, remember, the Vp from our last lecture here, Vp from our last lecture was the displacement of P. So the vector that points to P prime minus P is the displacement of P, and then if you divide by the delta t, you get the average velocity. You take the limit to 0, you get the instantaneous velocity of Vp, which is the derivative of just the vector Rp, the position from here to there is the derivative Vp. And so, of course, if acceleration is the derivative of Vp, then the double derivative of Rp is the instantaneous acceleration. Okay, so the question is the instantaneous acceleration, so of course we know the average acceleration doesn't need to point tangent to the path, but neither did velocity, average velocity, but the instantaneous velocity is always tangent to the path. But is that true for instantaneous acceleration? Well, it could be true, but it's definitely not something you would ever want to bank on. It usually isn't. The instantaneous acceleration rarely actually points tangent to the path, which is why acceleration is so non-intuitive and confusing oftentimes. because oftentimes you're moving in a direction that you're not accelerating in. You can imagine if you throw something up in the air, it's actually accelerating downward even though it's going up, right? Because gravity is accelerating, decelerating, pulling it downward, right? So acceleration rarely points in the direction of the path, okay? Okay, or even is tangent to it, right? Okay, so let's look at the acceleration of a point in a different way. Okay, so now say, this is the path it's traversing, and you've got the point P there, and we're going to define two unit vectors. Okay, we've got u hat t, which is the unit vector that points tangent to that path, right? And it's a unit vector, so its magnitude is 1, and it's always tangent to the path. That's what the t means. And then there's a unit normal vector, okay, that's also, its magnitude is always 1, but it's always perpendicular to ut, or perpendicular to the path, and it always points to the the radius of curvature, the center of a circle. So you take any spline line and you want to find the curvature at a certain point. At that point you put a circle tangent to that, and the center of that circle is c, and the radius of that circle is rho, which is the radius of curvature at that point. Okay, so that's defined here, rho. And then notice the angle phi is basically from the horizontal line to the unit tangent vector. So that's our definition there. Okay, and now that I've explained that figure, suppose we define the instantaneous velocity of point P, Vp, as Vp equaling s dot u hat t. Okay, so it's important to know that s is essentially the displacement along the path. So you could think of each of these little dashed lines as kind of a ds, a little increment of displacement along the path, which is of course infinitesimally small. If you divide that by delta t, the ds divided by delta t, it's the derivative of s with respect to t, and is essentially basically the velocity traveling tangent along this path is s dot, which is derivative of s with respect to t. Okay, and then of course it's if it's just a scalar value, as s dot is just the speed, you multiply it by u hat t, which is the unit vector tangent to the path. Now you have the vector Vp. Okay, so we're going to define it that way. Okay, so that's the velocity. Now say you want to find the acceleration of that point P, the instantaneous acceleration. Well, then you take the derivative of Vp, the vector Vp, and that derivative is AP, the acceleration of point P. Well, since we have these two things, s dot and u hat t, change as a function of time, they both do. When you take the derivative, you have to use the product rule of differentiation. So you take the normal one of s dot, and then you multiply it by the derivative of ut. You can see a dot in it, so that's the derivative of ut hat with respect to time. And then you add it to the derivative of s dot, which is s double dot, and ut just in its normal form. So that's the derivative of it. And that's a little interesting because you can see here, this term right here is basically the acceleration. S double dot, the derivative of the speed, is the acceleration in the direction that is tangent to the path. But you can see here, there's a very strange term that makes it not so tangent to the path, and it's also a vector. And so we'll find out what is that. Like I said, this one is the more intuitive one. It's just how fast you're accelerating in the direction that you're going along the path. Okay, but there's obviously another acceleration component to consider. Okay, but before we define what that is, let's throw out some interesting derivative math so we can start interpreting what this term actually is. So first of all, it's good to know that the derivative of u hat t, okay, with respect to phi, that angle, okay, is, of course, if you take if you don't have this be approaching 0, then you have just the delta u hat. So you can imagine from one instant to the next, if it was a finite delta t, the final ut, plus delta ut, would be in a different direction, and then the initial ut would be in the direction you see there, right? And so as it moves along the path, of course the magnitude of these things stay the same because they're unit vectors, So ut plus delta ut is still, the magnitude of this vector would still be 1. Its initial magnitude is, of course, 1 because it's a unit vector, screaming around that path there. And so you take the final thing, subtract it from ut, then you can see delta ut is this vector that points from initial to final, right? And you can also see, this was the initial vector drawn there with that phi, and then this is the delta phi. The final phi minus the initial phi is the delta phi there, okay? And so, again, if you take this the vector here, and that's a vector, which is why it's bold, the delta ut divided by delta phi divided by this delta phi, not a vector, okay, and you put the limit to 0, now you're getting the derivative of this. And so let's define what this is, okay? That's of course, this bottom one stays there, but the top one is this, which is a little confusing. So I'll step you through it. So if you have, say you take the phi, okay, so what we're doing is we're trying to find the magnitude of this, okay? And so the way you calculate the magnitude of that is to first recognize that the magnitude of this and this are the same. So according to math, of course, trigonometry and basic high school stuff, if these two are the same length, which happens to be 1, then the angles here are the same, okay? And this angle is, delta phi, right? So if you take half of delta phi, you take half that angle, and you go up here, this angle will be a right angle. If you take half of that, you have a line halfway through, this will be a right angle there. So you can take sine of delta phi divided by 2, sine is going to be this divided by 1, which is just this, right? Because you divide by 1, it doesn't do anything. So we times it by 2, and now we get that length, okay? So 2 sine phi, delta phi divided by 2, that is the magnitude of the length of this. Now you got to ask yourself, what direction does that point in? Well, you can imagine as delta phi approaches 0, as it gets smaller and smaller and smaller, then some interesting things happen. First of all, as it gets smaller and smaller and smaller, these angles approach 90 degrees. Because, right, you know that this angle plus that angle is 180 degrees. And you know these two angles equal. And so if this approaches 0, then you know both those angles have to be 90 degrees to add to 180 degrees. So pretty much as delta phi goes to 0, this is always going to be, this delta ut vector is always going to point normal to ut and be perpendicular to it, which is why we take the magnitude of it and times it by u hat n. Okay, that's how we know it's in the perpendicular direction of un, which is perpendicular of ut. Okay, but then of course we also know that as delta phi gets small, remember sine of an angle equals that angle if that angle is small, right? And so because delta phi is getting infinitely small and it's divided by 2, which makes it even smaller, then you can just ignore the sign, and it's like 2 times delta phi divided by 2. The 2's cancel, now you just have delta phi divided by delta phi, which cancels. So this whole thing, as delta phi goes to 0, ends up going to just u hat n. Okay, so it's interesting, the derivative of ut with respect to phi is just un. And that's useful. Okay, let's look at another interesting mathematical relationship here. S dot is, of course, ds divided by dt. Okay, and u hat t is, of course, this. U hat t dot is the derivative of u hat t with respect to time, which you can see is here. But using the chain rule, we can block these out. And you can see, those would cancel. So this is, this here in the parentheses might as well just be u hat dot. Okay, but we're going to break it into this using the chain rule so you can see how this would work. Now what we get is, and first of all, recall, the delta phi with respect to ds is by definition the curvature of a path, which is the inverse of the radius of curvature rho. And you might recall that from solid mechanics beam bending theory was where I first came across this, which makes sense because of course the more phi changes along a path for a short stretch of distance, the more curvy it is, the more curvature it is, and the smaller the rho is, right, to get a larger curvature. The smaller that radius is, the bigger the curvature. So This is derived in many other textbooks, but you can also get an intuitive sense that this would be true from what I just said. So, but anyway, trust me, this is well known in mechanics. Delta derivative of phi with respect to s, the distance along the path is the curvature of that path, or the inverse of its radius of curvature. Okay, so knowing this, we can plug this in for this and put 1 over rho. And you can also see this is ds with respect to t, so this is s dot, and that's also s dot. So you can start seeing up there, this ends up being just s dot squared from these two things, right up there, divided by rho from this. Okay, and then this guy right here, remember, is this, which is just un. So that's where the un goes. So if we go back to this equation here, this term that we're trying to figure out, this one's the obvious one, right? But this term, we're like, what is that? Well, it apparently equals the speed along the path that the particle's going in, squared divided by the radius of curvature, and that magnitude points in the un direction normal to it. So I don't know if that looks familiar to any of you, but if you remember from high school physics, speed squared divided by rho is the centripetal force. And of course, as you know, centripetal force always acts, if you're going in a circle or something, it always acts a normal to the path. And so that's exactly what this is. This is the acceleration along the path, and this is the acceleration normal to the path, and is the centripetal acceleration. Okay, so both those components add together, the normal component plus the tangential component, or this is the normal component, that's the tangential component, that's the normal component, right, to be the particle's acceleration, AP. Okay. And that's essentially what this says. Okay. Okay, so yeah, and we could write it like this or like this. Okay, this is the way you'd want to memorize it. The speed squared divided by rho, un plus acceleration along the path there is, two normal components added together is the acceleration. Okay, so let's do a quick example. What is the acceleration vector of the block at the topmost point P if it continually rotates about point P with a constant speed of 2 meters per second? So imagine you have a circle. Here's the center of the circle. Its radius is 4 meters. You've got a block up there at point P, and it's rotating like this. Okay, something like that. But at that instant there, it's moving at 2 meters per second. Okay, so I'll draw this again here. Okay, and so the question is, what is the acceleration vector of the block at the topmost point P? Okay, well, if it's moving at a constant speed of 2 meters per second around here, then you got to ask yourself, what's the acceleration tangent to the path? Well, if it's constant, then this goes to 0, because the derivative of a constant is 0, right? And then the acceleration of that point is that velocity, or sorry, that speed, which is 2 meters per second, squared, divided by rho. Of course, rho is the radius of that circle. Okay, so 2 squared is 4, divided by 4 is 1. So you have 1 meter per second squared is the magnitude of the acceleration at that point, and we know it's going pointing toward O, normal to the path. That's the centripetal force. Okay. So what about this example? What is the acceleration vector of the block at point P? If it accelerates in a straight line to the right, so say this guy's just accelerating, getting faster and faster, moving to the right, with an acceleration of 2 meters per second squared. Okay, well, you could say, well, wait a minute, you didn't tell me what the speed is at this instant here where it's at point P, but we kind of don't need to know it because, right, you need to know it here. If I said it's accelerating, you'd also need to know what the speed is at that point if you wanted to plug it in there, but you don't, because you know if it's moving a straight line, that radius is infinite. Okay, and I'll show you that in a second in the next slide. But if you have an infinite radius, okay, then this cancels out. It becomes, something divided by infinity is always 0, so that cancels out. There's no centripetal force, of course, because it's going in a straight line. And the acceleration we already were given is 2 meters per second squared, and it goes in that direction. So the answer is 2 meters per second squared in that direction. So it's kind of trivial. Okay, but just to talk a little bit more about curvature, if you didn't understand why in that last example the radius of curvature is infinite, if you want to find say you have this random line or spline line and you've got a point and you want to find what's its curvature there, like I said, you draw a circle that's tangent to it, and the radius of that circle, rho, is the radius of curvature. And 1 divided by rho is curvature. Okay? And you can think of it, if it's very curvy, then the rho is small, because 1 divided by a small number is big. And as rho gets larger and larger, 1 divided by a larger number means the curvature gets smaller and smaller, until finally, when the radius of that circle is infinite, it's no longer a circle, it's actually a straight line, because 1 divided by infinity is 0, and we know that lines have 0 curvature, they're linear. So, said another way, a circle with an infinite radius is a line, or a line is a circle with an infinite radius. Okay? And then just remember, curvature is also defined as the derivative of phi with respect to ds, which we talked about before, and I told these in other textbooks. And make sure you convince yourself, of course, for something very curvy, that phi is going to change a lot over a small distance, and so you can see that ratio would also correspond to that. Okay. All right, so let's look at angular acceleration. That covered acceleration of a point. If a point's moving along some path, whether it's straight or curved or whatever, you have to consider both components of centripetal and tangential acceleration. And some of those may cancel, but oftentimes they don't, and you have to consider them both. Okay? And just the big takeaway is the acceleration rarely points in the direction of the path, okay, or tangent to it. It's usually off in a different direction, which makes it very non-intuitive and complex. Okay, so let's look at angular acceleration here. Okay, so angular acceleration is if you take, first of all, the angular velocity of some body, omega, and then you let it move some delta t later. That angular velocity moves to a different, say the axis of rotation moves to a different spot at some omega prime. Then you take the difference of those angular velocities, you get delta omega, which is the change in angular velocity. Okay? And then if you take that change in angular velocity divided by the delta t, the difference in time between those two omegas, then you get the average angular acceleration. And of course that doesn't point typically in the direction of the omegas, okay, because you take the difference of them. And as delta t goes to 0, you get the derivative of omega with respect to time, or omega dot is the angular acceleration vector alpha. Okay, so alpha is a vector, and it's the derivative with respect to time of the angular acceleration, omega dot. Okay. And does that point in the direction of omega? Well, again, very rarely. You could imagine, here's one omega, and then a few seconds later, there's that omega. It's rotating around that. You take the difference between those, it's going to point in a totally different direction. But the trick is that for two-dimensional or planar mechanisms, like the ones we've looked at almost exclusively in this class, and is the most common mechanisms that just links that move in a plane, right? You'll notice all the omegas in a planar scenario always point in or out of the page. But the point is they're always normal to the plane. And alpha is no different, okay? Alpha for 2D planar scenarios is always going to be pointing out of the plane, normal to the plane, and just with omega. But that doesn't mean they're pointing in the same direction. For instance, imagine a block that's rotating, really fast, and then a delta t later starts slowing down, but it's still rotating the same direction according to the right-hand rule. Well, if you take that initial omega and subtract it from the final omega, you can imagine the acceleration is going to be into the page going this way, and that means it's decelerating. So in that case, yes, both the omegas and the alphas are pointing normal to the page. They're not going the same direction. The alpha is going the opposite direction. Now, of course, if it's accelerating, then they're pointing the same direction. Okay, so just something to think about. But that's just for planar scenarios. Usually for three-dimensional real-world scenarios, they point in completely different directions. Okay, So that concludes that topic. Okay, so now we're going to talk about, acceleration difference equation. This is like when you're marching from, remember the velocity difference equation, you go from point P to point Q on the same body, but they're not coincident, and you want to march from some velocity at P to the velocity at Q, 2 points on the same body. Okay, so just like I said, imagine this block here. You've got a point Q, you got a point P, and you want to find the velocity of P, but you have the velocity of Q, and you have the angular velocity of the block with respect to this ground here, right, omega. Well, the velocity difference vector is that omega, which for this planar case comes out at, as normal to the page, cross RPQ, which is the position difference vector that points, from Q to P, but it's RP minus RQ. Okay, so omega cross that is the velocity difference vector. And remember, that's the velocity of P caused solely by a rotation about Q. The linear velocity of P caused solely by the rotation about Q, which for a planar scenario, that axis of rotation always goes through Q and is perpendicular to the plane. Okay? And then, if you obviously add that velocity difference to VQ, then you'll get VP. So that's how you march from Q to P, from two different points on the same body that aren't coincident. Okay, that's just a review. Okay, well, to find the acceleration difference equation or the acceleration difference vector, we can. So just to be clear, this is the velocity difference vector, but this is the velocity difference equation, right? So we take the derivative of the velocity difference equation to find the acceleration of point P. Okay, so we do VP dot, so it's VP with respect to time, derivative with respect to time, and that would be, if you take the derivative of VQ, you get VQ prime, so it's derivative of VQ with respect to time. That makes sense. But then, how do you take the derivative of two vectors cross-producting with each other? Well, you basically use the product rule the same kind of way as you do if you have two functions multiplying by each other that are both functions of the thing. The variable you're taking the derivative with respect to. So you have to use the product rule. So you take the derivative of omega, or the normal one of omega, to cross the derivative of RPQ with respect to time, plus the derivative of omega cross RPQ just left normal. Okay, that's the product rule for taking the derivative with cross products. Okay. Okay, so let's simplify that. First of all, recall that the displacement difference vector is, if you take the displacement of P and the displacement of Q and subtract them, then you get the displacement difference vector, which is how much P would translate caused solely by rotation about Q. And it's also, if you take the position difference vector at the delta t later, the prime thing, and subtract it from the initial position difference, we prove that they're the same thing. Okay, so if you want to find out what this term is, RPQ, with respect, take a derivative with respect to time, that's what the dot is, or this, right, where delta t approaches 0, so drpq over dt, or rpq dot, which is written there, then you could see that, if you take the derivative of these guys with respect to time, you're going to get vpq, which is basically the velocity difference vector, right? If you take, if this value right here is how much P has translated caused by rotation about Q, then if you take the derivative with respect to time, that's the velocity difference vector, how much P's speed is going with a linear velocity caused by the rotation about Q. And we've proved, excruciatingly in topic 2, that is omega cross RPQ. Okay? So basically we can take this equation here, and simplify this. So you have VP dot is AP equals VQ dot is AQ plus, now here we do omega, right there, cross this dot, which is that, so you plug it in, plus what's omega dot? Well, remember omega dot is just alpha. That's the derivative of angular velocity with respect to time is angular acceleration cross RPQ. Okay? So that is the acceleration difference equation. Okay? And it's just the derivative of the velocity difference equation, right? But as is characteristic with acceleration, there's some weird terms here. you might have expected it to just be the velocity, or sorry, the acceleration of q plus the angular acceleration cross rpq. Then it would be similar to the velocity difference equation. But there's this other strange term that pops out when we take the derivative, largely because of the product rule.